we'll talk design that is able to put and make also. Then we work with quantum dots. Okay, originally we were that cadmium based system, but now we are not working on that because there are toxicity concern. Cadmium is toxic. So now we are working, one of the major contribution from our place is silicon Si quantum dot. Silicon is also a semiconductor. And so if you look at them, we'll come to that. So that's the countries. Then we work with other kinds of safe quantum dot like copper indium sulfide, that one. We make with magnetic nanoparticles, which could be iron oxide nanoparticles. We work with rarer doped nanoparticles that has this property of transforming light from one color to another. We work with silica nanoparticles. So ordinary silica is SiO, with 4 oxygen bridge, right? That's sand. And when you say nanoparticles, it's sort of like nano sand, right? Silica nanoparticle. But another variation of that is where one of the SiO group is replaced with just SiR, organic group. There is no O, okay? So that point, it doesn't branch out, connect to other silicon. That's why it's called organically modified silica. So it is only has 3 oxygen bridges, SiO, SiO, Si, and the other one is organic. That organic group, you can put different functions. So it's kind of, you can say it's like soft sand, because they're not 4-dimensionally bonded, only 3, okay? So that's, we do, it's called organically modified silica. So we work with that. And that also you can prepare by sol gel chemistry, hydrolyzing and doing it. Then polymers, and my cells are just lipid structures that you can manipulate. And then we only talk, so these are a whole range of nanoparticles, some of them organic, some of them inorganic. Now also the important emphasis is combining them together and making organic, inorganic hybrid nanostructures. So we work with a lot of them also. Okay. So then you can say again, well, when you're making these nanoparticles, what matters? What properties you need to address? One of them is the chemical makeup. You want to make sure that the elements that you are incorporating are not toxic, they are manipulable, they have right properties, and that's what I said, that you don't want to use cadmium-based nanoparticles, for that purpose, okay? Shape matters, okay? Some people claim that if you take a rod shape, they can have easier penetration inside the cell. Yes? Well, it depends. For example, if you want to do photothermal therapy, then the nanorods and the nanostars are much more effective.
But to make it biocompatible, we have to surface coat with any other polymers. But when we coat with the polymer, does the shape remain as it is?
Well, it depends. Suppose if you're putting a few layers of this very thin coating, then the characteristic will be maintained, in the shape will be maintained. Yeah, because the chemistry you do, suppose you have metal nanoparticles, the chemistry you do is not going to affect that metal composition. Okay,
so for example,
there is no chemistry.
Nanorods or nanostars, we surface coat them with a polyethylene glycol. When we coat that with polyethylene glycol using the thiol chemistry, will the shape of the nanoparticle will be the same as the nanorod and nanostars itself?
Overall shape will be the same, because if you have very thin coating of that, if you put large coating layer, then slowly and slowly the rod will try to become spherical. Yeah, but if you're just putting a surface layers to couples, like to make it more biocompatible, put pegylation group or put targeting group, they will remain the anisotropic like this. And the gold doesn't change. Even though if you put a very thick layer, the gold doesn't change from rod to a sphere. Because the chemistry you're doing, it does not dissolve gold and make it shape.
It covers the shape nanoparticle of 4 nanoparticles.
Yeah, but what I'm saying is, again, if you use a thin layer just to coat like surface coating, then it will maintain the shape of the gold original rod. But if you go to thicker and thicker layer, maybe they will deform and become spherical. Okay. But you don't need to put a very thick layer, because then you may be self-defeating the purpose of using gold nanorod. Okay, so shape is important. Size, as I already told you, we talked about it, that when you're making inorganic nanoparticles that are not biodegradable, my advice is to keep it below 10 nanometers and use them. Okay, you can use many of the nanoparticles together, but a single nanoparticle should be not more than 10 nanometers. Okay, if we are making polymeric nanoparticles that can be biodegraded, then you can have anywhere up to 100 nanometers. So size is important, then porosity, then also charge on the nanoparticles. So one of the ways, if you have a larger nanoparticle, let's say 100 nanometers, very often the problem is that these nanoparticles in course of time will aggregate and settle down. Okay? And that aggregation can be a major problem, because then these suspensions are also called colloidal suspension, because these are nanoparticles. You use them in dispersed state. You don't use nanoparticle solid and inject. You have dispersion in water. So what happens is that you put some charge on that. And charge is what you can measure. It's called zeta potential. You measure that potential by using, light scattering, DLS, dynamic light scattering. So if you do that, so you want to make it positive or negative or neutral depending on what you want to do. But very often, if you have too much of negative charge, it doesn't get inside the cell. So you want to keep it neutral or slightly charged, not a lot of charge. Okay? And then surface should be acrylic overall to disperse in water, and that you do by surface coating. So chemists can make contribution in two ways. One of them is making the nanoparticles, and the other one is surface chemistry, to treat the surface, to make them biocompatible, dispersible in water, having appropriate amount of charge in the surface, all these through surface chemistry. Less solubility? No, it depends. It depends that inner side is hydrophobic. There are ways you can coat that to make them dispersible in water. Again, that's a very simple thing for chemists to do. To how you can modify the surface by appropriate surface coupling chemistry. Okay. So this is very important part of nanomedicine to do that. Now you can also, in addition to designing the nanoparticle for drug delivery, you can also put other functionalities in nanoparticle which will enable you either for imaging or for therapy, added therapy. Okay? So it's not just have to be a carrier. It can be an active component that does also therapy. So optical we already talked about, that how we can do sensing and imaging, but we will also talk about light activated therapy in a minute. then you can also make those nanoparticles thermoresponsive, thermally, okay? And so we can tailor their thermal characteristics for either thermal imaging or for thermal activation of drug release or photothermal therapy, all three. One example we will look at is gold nanoparticles, that when you shine light, that it can couple into the plasma and resonance, it generates a lot of heat locally. So gold nanoparticles are very effective nano heaters, and you can use it for thermal therapy, photothermal. So when the gold nanorods get into the cancer cell, they are localized, they are not in healthy cells. You shine light, the light is absorbed by gold nanorods, it raises the temperature locally by 20 degrees or so, the cell is dead. Okay, that's called photothermal therapy. For what? Hypothermia? Hyperthermia. Yeah, that's what he's saying. Photothermal therapy is hyperthermia. Raise the temperature of the cell high enough, the cell dies.
So gold nanoparticle can be used?
Yes. Well, it's not can be used, it's being used. There are already clinical trial in humans for certain kind of cancer to use this. Okay? Then you have magnetic. So you can use magnetic nanoparticles like iron oxide, or we work with another material. They are to actually are nanoparticles or nanoformulation of semiconductors. And I know most of you are not physicists and may not have taken physics course, but semiconductor has two bands for electrons. One is each energy level is characterized by a wave characteristic called wave vector. So you have a band of filled electrons, which is a valence electron, and then you have a band of empty electrons, phosphorescence. And the difference in the semiconductor between phosphorescence and fluorescence is a little mixed. Okay, so that's one thing. The other one is that the electron is here now, but it leaves a hole, a gap over here, because the electron has gone from here to what's called electron hole pair. Pi states and pi star states, or you can have n state, non-bonding, and pi star states, and you have this gap. So you get many of these localized levels, and you can actually have electron going from one localized level to another. It's like molecular transition. In this case called excitonic transition, because the hole and the electron now they're both localized, they're confined, they cannot separate. Okay? So one thing is that if you, I don't know how many of you have taken quantum mechanics course or quantum chemistry course, but first thing we talk about quantum effect is we talk about particle in a box, one-dimensional box. That if you confine the particle in a one-dimensional box, what happens to the energy levels? They become discrete energy levels, okay? And then the gap between the levels is dependent on the length of the box. As the length is small, the gap is big. The length becomes wider, the gap becomes smaller. Size tunable. Same thing happens over here. This is like a box. You have tracked the electron on the hole. Okay? And as the particle size becomes bigger, this gap becomes smaller. What does that mean? That means when it emits light, the emission is to be at longer wavelength, less energy wavelength. Okay? And when the particle gets very small, then energy gap is bigger. The emission is at higher energy, that means shifted towards UV, right? Higher energy, shorter wavelength. So you have size dependent optical emission. So you can use the same material, let's say cadmium sulfide or cadmium selenide, And same material can be actually used with different size to emit different colors. How do you get different colors in dye? You have to, one dye can only give you one color. So that's the beauty of quantum dots. The same chemical composition, you want to vary the condition of growth, that you stop it at this size or this size or this size. You get all this tunable emission, right? Antibody can carbonize. Picture breaks down when you go to nanoparticle. There is no band like this. You have states like this on top of each other, right? And emission then becomes allowed, coming out, right? And this is again size tunable, depending on what is the size of silicon nanocrystal, okay? And what is another beauty of silicon is that silicon is biocompatible, okay? Our body has a lot of silicon, okay? And the other thing is that that silicon, but that you can put not only silicon, which is maybe 3, 4, 5 nanometers, but you can put iron oxide nanoparticle that can register by magnetic resonance imaging. So same one, you have silicon doing optical imaging, and iron oxide, which could be 10 nanometers or so, doing MRI. And the same one, if you want, you can put some drugs over there for drug delivery. When it breaks up the polymeric nanoparticles, delivers drug. So there are many functionalities. So this is what hierarchical structure. So you have one nanoparticle encapsulating another nanoparticle, and that may be encapsulating another one. So you can build not only a pouch containing these in a small, but you can also build core, shell, 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 right? Multiple shells. This is where we can use what we call hierarchical nanochemistry. So firstly, you make a core with a chemistry. We'll talk about that in a minute. And then you change the condition. And now your nanoparticle of certain size that you have made acts as a template. And you do this template chemistry so that something else forms in there. Okay? And then depending on the amount and condition, you form this. And then you inject another reactants at maybe slightly different temperature or condition, and that initiates another reaction of a shell. Okay? So you can make core shell structures. Right? Yeah. And these are the things that is a good thing you're thinking. You need to think about some of these and apply clever chemistry to make all kinds of structures that can have different applications. Okay? Any other question? Okay, so let's move on in this. So so a little bit of chemistry now. So one popular method of making quantum dots, let's say for example cadmium selenide, is this is called hot colloidal synthesis. So you have a boiling solvent, which is a high temperature solvent, and in there you inject, let's say, this cadmium salt, which could be cadmium chloride or something like that. They get in there, and this is in the inert atmosphere. Then you raise the temperature, okay, and then inject selenium precursor, which could be selenium, elemental selenium dispersed, or it could be some soluble selenide, and they get in there in ions, and under the certain temperature, then the ion exchange occurs, and what will happen, you will form cadmium selenide. Okay? And then you also have a surfactant molecule. A surfactant are these ligands, and on one side maybe it has group to couple to the cadmium sulfide surface, and the other one could be non-polar group to disperse in organic solvent. Generally, they're doing it in organic solvent here. So what will happen is that you will form, there are two competing processes. One of them is where the ions are combining and growing as a nanoparticle. So it's nucleation and coated with a stabilizing ligand. Okay? Yeah. Acha. So, and this is now very well established method. So you can really make these nanoparticles a very uniform size. And that's what is called monodispersed systems. So for biomedical application, you want to make them monodispersed, but also for optical properties, because if it is not dispersed, one size is this, another size another. One side may be emitting this, another size may be emitting here. So you have broad emission. You cannot use many different emission channels, narrow channels. Okay? So that's why you need to make monodispersed, but also for biological applications, well-defined characteristic means you need to have monodispersed. So your system should be within 10% of dispersity. Okay, plus minus 10, maybe better plus minus 5 even. Okay? So what are the stabilizing ligands? Very often they use oleic acid. Okay, stabilizing agent, precursor, temperature is 300, emission range that you can tune is from 480 is environmentally friendly chemicals. So here is so green chemistry and low temperature, not 350 degrees, but lower temperature. And the coupling group, not a coupling group like oleic acid that has long chain fatty, but using a small one to trap it, cysteine, stabilizing and making this, can be dispersed. And then later on, so if you use cysteine, this is also water dispersible because it has amine and it has acidic group. Okay? So you can, because eventually you have to make water dispersible. And you can also use coupling to conjugate with antibody. They're highly luminescent. What if we make an organic phase solution, like hot colloidal synthesis? Then you have to exchange the ligand to make it water dispersible. So one of the things is use the, derivatizing with mercaptodecanoic acid on the surface, and then coupling it with lysine, which is amino acid, to have the carboxylic group exposed outside to make it water soluble. Okay? So hydrophobic attraction occurs between quantum dot and alkyl phosphine ligands, and then you can disperse and functionalize to hydrophilic block. Okay? So another part you want to do is that you need to couple it to antibodies, remember? To target certain antigens. So how do you use antibody on the surface? So this is what's showing that if you have carboxyl group, you can actually connect through this and the surface chemistry through this coupling. Okay, disulfide reduced, and then meet on the surface, form a stable thiol linkage, or you can use another chemistry over here. So these are the chemistries you use to couple surface chemistry of conjugation. Another method we use, which is dry chemistry. Dry chemistry is where you actually can use a precursor gas. So in this case, we are making silicon quantum dots. This is our technology that we do it in our place. So we took silane gas, SiH4, and with a hydrogen carrier, it goes in here. Then there is a helium buffer gas in there, and you use a laser, carbon dioxide laser, that pyrolyzes this. The laser light is absorbed, it chemically breaks the SiH bond. So you have silicon atoms, and now they combine together to start forming silicon nanoparticles. So that silicon nanoparticles now are, we adjusting the flow and concentration. You can make a certain size, and they are then carried with the gas up here. Now hydrogen does a couple of things. If you leave the silicon surface exposed, what will happen? It will readily oxidize. It forms silica coating. Okay, and forms silica coating, it tends to reduce its efficiency. So very often what happens is when hydrogen also passivates the surface. So he puts a layer of hydride on the surface to protect it. So it forms a hydride, silicon hydride, and it doesn't oxidize readily. And then what we do is these materials are not monodispersed. They have a long, different size distribution. So what we do is, in this case, we use the acid, nitric acid or others, to etch the surface, clean the surface, and also reduce its size to the size where their emission is very strong and a certain color. And then after that, you can again hydrogenate and then use this coating of this material, the alkene, certain kind of alkene, to cover it, and then with UV light polymerize it. So it's a polymer coating over here of this thing, and then you can have many nanoparticles with these R groups, hydrophobic groups, enclosed in a polyphospholipid. Okay, phospholipid surfactant enclosure. So this is the example I was talking about, many small nanoparticles in here coated with a bigger envelope. So this gives you a little more chemistry of how we prepare larger size, we etch it to a smaller size, and then we can utilize it with nitric acid, utilize it and coat it with phospholipid and make the nanoparticle dispersion. Another one is this organically modified silica chemistry. So this is what is known as solvent chemistry, a very, very widely used method to make glass through chemical means, or silica through chemical means. So how do we make it? And then eventually the gel, when the network extends, they become solid. But the solid is still a little viscous, and you need to densify it. It has pores inside, and that is also sometimes called porous silica. But what we found, which is more useful for biology, is that we actually only have trialkoxy silicon, and this group is an organic group with a double bond. Okay? Or this is VTES, or you can have another one with some other kind of organic group with a functional group at the end. This functional group can be either deuterium for imaging, vibrational imaging, of fluorine-19 for MRI, or it can have radioactive group for PET imaging, which is called positron emission tomography, very important imaging modality, or a single photon, the correlation tomography. So you can make different plots over here. Now if you use this or this, and you hydrolyze and condense like under basic condition, what happens that you form only a network in 3 directions. this direction cannot hydrolyze organic group. So on the surface, when it forms, you have, suppose you are looking at the case over here, where you can actually have this medium, say, is hydrophobic or hydrophilic, then the polar groups will be out and it will form a micellar structure where inside will be the organic. Or depending on if it is organic, then outside is organic, inside is inorganic. You can tailor the surface characteristics of the nanoparticle that you form. Okay. The other way you can make is, and then by varying the conditions again, you can control the size. So this is one way of making silica-based nanoparticle, but we make it one with organic functional group that we can do different things with, and that is what we call ormosil, organically modified silica. Okay. The other way you could do is that you can form a reverse micelle. The first micelle is like, suppose you take some kind of long chain fatty acid, okay, and which is like AOT in this case. And what happens is that when you disperse them, let's say in water, then what happens is the outer side is pointing out is carboxylic acid, and inner one is the fatty chain, and they form this spherical pocket where inside is hydrophobic and outside all these are what you call hydrophilic group, and that is called micellar structure. So in micellar structure, if you inject this, this can go inside a hydrophobic domain, and when you hydrolyze, it grows inside there. And the nanoparticle can only grow to the size of this pocket, cavity. So this surfactant micelle acts as a nanoreactor. You have reaction vessel, that's a nano size. You hydrolyze, make it, so your nanoparticle can be of the size of the reverse micelle or micelle. And then if you do reverse micelle, then you can have the reverse configuration. So anyway, we prepare these nanoparticles. So one of the configuration we make, like over here, you can polymerize, polycondensation. Then you get this with a double bond sticking if you start with this. Another formulation where we use this kind with NH2 group, then when you hydrolyze this one, it gives you this, and then you can, or you can start with a double bond and add this one to this, it will grow and put amine group on the outer side. And we have used this nanoparticle for gene delivery because DNA is negatively charged because of the phosphate groups over there. An amine group under certain pH condition is positively charged, so they can electrostatically bind. So this nanoparticle on the surface can grab DNA and deliver DNA for gene therapy, or it can grab siRNA that they're gene silencing, and it can. So you can also do gene silencing, and inside over here you can load it with drugs. So do gene therapy and do together. You can also use chemistry to not only make a spherical nanoparticle, but to make it also elongated in different shapes. And that's a very active area also, how we make things of different shapes. So one of them is making gold nanorods. Gold nanorods has a lot of applications we'll talk about later. So one of the ways they make it, that there is this surfactant that pushes them to grow in a certain direction, elongated direction. It's called CTAB. And so when you use that surfactant and through gold precursor and reduce it, it firstly forms gold nanorods, and that acting as a seed with this surfactant pushes it to make a rod shape. Okay, So choosing a C type here, acetyl trimethyl ammonium bromide. That's the kind of, so this is the polar group, this is a non-polar group, and that pushes anisotropy. So it's a very common method of making gold nanorods. But gold nanorods then are coated by this surfactant. This surfactant has proven to be toxic. So a lot of effort now is that when you make gold nanorods using this, you need to replace this. Otherwise, a lot of toxicity can come from here. Okay. This gives you an example of how you control the surface charge. So when you have made through this with this organic group, it has over here carboxyl group, which may be negatively charged, and by balancing it with ammonium salt, you can actually, mixing the two, you can control the charge on the surface, okay, depending on the ratio. How do you co-encapsulate, like you were asking question earlier about it. So here is one example where we had quantum dot and iron oxide, and then we could incorporate that into the ormosil structure. So we mix these two nanoparticles in here, and then we add these precursors of this organically modified silica to grow cells. So you do sol gel chemistry after you have made these nanoparticles, and then you can incorporate that in there. So now I'm going to talk about some of the characteristics of these nanoparticles that we can use for imaging or therapy, and then we will take example of some of the therapies that we do. Okay, nanotherapy. So one of the nanoparticles we make, these ones we make through like similar to this colloidal chemistry, which is very, very simple, is these nanoparticles. Sodium ytterbium fluoride with thulium as a dopant, varying concentration. So the thulium substitutes ytterbium at certain sites in nanocrystals. And another one is where you can have erbium. This ytterbium can be replaced with yttrium. You can also have not only a core, but you can put an inert shell of calcium fluoride. Calcium fluoride is very biocompatible, so we can put that thing over here. So these ones, actually, as I said, can be if it involves synthesis. You may do NMR and look at functionalities and others. So you make a nanoparticle elemental. Then you can also do some surface analysis, surface profiling, whether what do you have in surface, whether it's an oxide coating or this is all or what. Okay, so that's one thing. Then you are going to disperse it with ligand exchange in water, and you want to know whether the size is the same, or they have aggregated and become bigger particle, or the size has grown because of surfactant on the surface. So what do you do then at that place? Well, before that, you firstly do TEM, transmission electron microscope, of these nanoparticles in dry state. They tell you the size, shape, all these you can get picture. Then when you disperse it in water, you do DLS, dynamic light scattering. That gives you what is called hydrodynamic radius. What is the size of the effective particle that is like colloid dispersed and a scattering light? Then you measure the charge on the surface. Okay. So if you are making nanoparticles, you need to have some way to characterize its chemical composition. And I don't know, in India there are places where you can send the sample. In America normally we send it to some place and they chemically analyze I'll send you the report, what is the elemental composition. And then there are labs where we do surface profiling by different surface SIMS and other kinds of technique, and then after that we have a central facility where we say TEM. So where can you do TEM in this country? Are there any in Allahabad TEM facility? Huh? So where can you send? Because you need to know what is the size of the nanoparticle. So there is a service facility you can send and charge. So that's not a bottleneck. You can do that. And where can you do dynamic light scattering? So is it like also paid facility that can do? So all these, you don't need to have your own lab, right? And you go the steps of characterization, sending, maybe it's a matter of time. It may take you 6 months to have complete characterization.
Sir, I have a question.
Yeah.
For example, sir, if there is any extract, one of my students working on it, extract. Now we don't know there are so many different components in that, different constitution chemicals are there, and we have prepared, went for the synthesis of nanoparticle, and we have synthesized nanoparticle. So suppose there are 10 components, 10 components. Now we are not knowing which compound has actually reacted with the which has formed the nanoparticle. So, sir, how we can characterize that?
Well, firstly, look, there are 2 steps of preparation. One is you may want to be making certain kind of functional group, like I just said in Ormacil, you want to design these kinds of structures, that organic components, or you go in here, this R group, this part, right? That synthesis is organic synthesis.
No, sir. So I'm talking about suppose we have some extract. Suppose we take taking a plant extract, simple, like methanolic extract.
Yeah.
And in methanolic extract, there are so many different constituents. And particles are there. And we have taken, suppose, methanolic extract. Then we have gone through the synthesis silver nanoparticle. And we have synthesized nanoparticle also. It is coming in that range. We have characterized it. Now the problem is we don't know which compound is reacting to form the nanoparticle. That is the problem. This is one of the objectives of one of my students.
Yeah, well, I think that, I see your point, what you're saying, but you need to then characterize by a spectroscopy, or coupled with elemental analysis of your sample, because now you're talking about like which reactants have combined to form.
Yes,
and there are only, if you're making silver nanoparticle, you have to have a silver source. A silver source, I don't know your sample because I don't know what is the precursor. The precursor, if you analyze, you know which reactant has silver. If it doesn't have silver, the reductant to reduce it, it is not going to provide silver. Okay? So if you you got to dissect this problem firstly, starting with analysis of your sap or whatever you have, plant extract or sap, what are the constituents? And
suppose in the extract we have polyphenols and we have alkaloids also, and then we have saponins, steroids. Then we have to discriminate that this is reductant, it can act like this. We have to mostly all of these are going to act.
But look, you are asking, there you can do precipitation, you can do filtration, you can do all kinds of things, right? And you can also use size selective precipitation to fractionate certain size of nanoparticle in one place, certain another condition. This is the one that provides the lock and key. Okay? So you can, look, these ones you don't need to manipulate. There are lots of companies that sell antibodies, and you say what chemistry you want to have to couple, let's say this part over here, like NH2 part over here, you want to couple that to your nanoparticle. You want carboxyl group terminated, you want thiol group, you want what group you want on the antibody. To conjugate, they will make a decision, I want this antibody with this coupling group that I want to conjugate to the surface through chemistry. So that in chemistry, there are lots of papers and books that tells you how to conjugate to an antibody, okay, with either carboxyl or SH group or NH2 group. There are different kind of chemistries that you can use, and that going back to this, or dye, or we can put genes for gene therapy delivery, or we can put, and we need targeting group to target certain type, and another very important surface group will have a tendency to go through spleen and kidney and get out, okay?